Now, with a sufficiently large corpus, like the web, we're going to need to parallelize our query plan across multiple nodes. To begin the question of how to parallelize this, we have to think about how to partition our data across nodes. There's two obvious ways to do it. In the first scheme, we partition the inverted file by doc ID, so node k gets all doc IDs that hash to the value k. And when you see it this way, each node essentially is running its own little search engine over its own little subcorpus. So we get the same index and the same query plan that we had in the previous slide partitioned on a subset of the documents. And each node runs a query on the set of documents that it has. So you send the query to all the nodes. Each node computes its local top k and ships that to a central node, which can then sort the top k's from all the nodes and choose the true top k out of those. Okay? Now, if you want to make this a little bit fancier, particularly if you have a large number of nodes, you can come up with a multi-round scheme in which the central node says, I'd like to get the top very few from every node, and then incrementally probe the nodes for further down their top k lists as we go. And there's schemes for that in the literature, but for now the simple version is just we send top k from every node to one place, and that one place sorts and chooses its top k. The alternative scheme, scheme 2, is we partition inverted file by term so that node k gets all the terms that hash to the value k. And in this case, we get a picture like the one in the bottom where a particular node might be responsible for the term Berkeley, another node might be responsible for the term database, and a third node might be responsible for the term research. And now we have to compute a distributed join amongst all three of these nodes, merging their doc ID lists together. And that can happen with a variety of distributed join schemes. So it can happen in parallel, or we can simply ship the results of all of these index lookups to a single node for joining. Before we talk about the pros and cons of these two schemes, I want to talk a little bit about how terms get distributed across documents more generally. So this is a little side trip, but there's a fascinating article from the middle of the 20th century by this guy named George K. Zipf, and it's got the very general title, Human Behavior and the Principle of Least Effort. And the argument is that many things that humans do face a particular distribution, which we now call the Zipf distribution. And in the Zipf distribution, if you take the x-axis and you order the items that we're discussing by ranks from the most popular to the least popular, left to right, and then you plot frequency of popularity for these items, you'll get a picture like the one on the left, where the first highest ranked things are very popular, and then you get a long tail of unpopular things or equally unpopular things. This is very similar to what's called the Pareto principle, or sometimes the 80-20 rule, in which 80% of the probability mass falls in 20% of the terms. A simple way of saying it is some things are hot and many things are cold. Okay? When you take the log of the Zipfian distribution and you plot log frequency against log of rank, you get a descending straight line like that. More generally, this class of functions are called power laws. They're laws where we have a function of the form y equals ax to the negative k. Okay? And that describes the curves you see above. Well, when you have these hot-cold distributions or these 80-20 distributions, this affects the way that we want a partition work. All right, and keep that in mind as we talk about the pros and cons of these two schemes. So our first scheme, revisiting our first scheme, one of the cons of our first scheme is that every query gets broadcasted to every node. Because every node may have the term Berkeley, we have to send the query for Berkeley to every machine in our network. Now, the truth is that nodes that don't have Berkeley do very little work. They do a lookup in their B tree, they find no matches, and they're done. Only nodes that have matches are going to ship matches back in the top K query. Okay? So it's not that much work, but it is a bit of a bummer that we have to send every query to every node and do a little bit of work on every node. The second scheme, where we partition the inverted file by term, has the con that popular terms will make the nodes that hold them very busy. So if you're the node that's responsible for Bieber, you're going to get a lot of queries and you're going to have a lot of documents. If you get the term database, you'll have fewer queries and fewer documents. And it's very hard to mix up your terms across these hash functions to ensure that you get a balanced load across machines. In this case, when things are bad, they're really, really bad. The hot nodes will be very, very hot and really won't run efficiently. And so the Zipfian distribution kind of works against scheme 2 and causes us to choose scheme 1 as a more sort of stable and reasonable scheme for dealing with workloads of data and workloads of queries.